Today we're going to move on and continue looking at absolute value. And our topic for today is absolute value functions. For my students who were in class today, we began with a little bit of a discovery exercise. In their table pairs, had them sit down and graph two functions by making a table of values. The function y equals x, and then the function y equals absolute value x. They all played spot the typo, and they noticed that I put -2 twice in the x column. That obviously should be -1. And so the students sat down together and they recognized that when y equals x, whatever x is, so is y. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. They plotted those points. And thus graphed the function. Students also sat down, and a handful of them needed a little bit more help with this, but a reminder that we're going to go ahead and substitute our x value in place of x in the function, and we can see that this function calls on us to take the absolute value. So absolute value of -2. How far away is -2 from 0 on a number line? 2 units. So -2, 2. -1 is 1 unit away from 0. 0, 0, 1, 1, and 2, 2. So most of the students, with a little bit of assistance, were able to create this graph. I asked the students then in their table pairs to take a moment and think about what they noticed about the graphs and what kind of questions that brought up. What do you notice? What do you wonder? If you're in my class and you're following along, you'd like to maybe give us some thought to that, take a moment now, pause the video, and you can write your answers in on the bottom of your note page. Among the things that my students noticed, in particular, they noticed the difference between the two graphs. One they recognized right away as a linear graph, a linear function, a straight line. This graph they described in various ways, and we've been working on the standard of mathematical practice that is attending to precision, and so they were kind of careful about how they described this. Some called it a V-shape. One student says it has a bounce in it. Another student says it changes direction. But they definitely noticed that there was a difference in the shape of the graph for a linear function versus this function y equals absolute value of x. After a while, after we exhausted everybody's noticing and wondering, we did point out a couple of other things. The V-shape, obviously, and then also that this absolute value graph is symmetrical, that the 0, 1, 2 values are an exact mirror reflected across the y-axis of the 0, -1, -2 values. And that became important to us a little bit later on. One student who'd been paying a little bit of attention in Algebra 1 asked if this was a graph that had a vertex. I said, yes, in fact it does. Invited my students to go ahead and flip this page over to the back side where we defined vertex. Now, in the next unit, we'll be taking a look at quadratic equations and quadratic functions. We'll look at their graph, a parabola. I explained that vertex will have a slightly different meaning when we start thinking about parabolas. But for this course, for this track, and for the textbook that we use, we're going to say that the vertex is the common endpoint of the rays that make up the graph of an absolute value function. So we had two main goals in class today. One was to be able to evaluate an absolute value function. Another is to graph a simple absolute value function. So we started off here, evaluating a function for two given values of x. In this case, when x equals 1 and x equals -4. Again, working in their table groups, I invited my students to go and evaluate these functions. We mentioned that right inside the word evaluate is the word value. For the students who weren't sure what they were being asked to do when I say evaluate, what is the value of this function? What is its worth for a given input? So once we were able to do that, talking about function notation, f of x equals absolute value x plus 3. When we substitute in 1, we say f of 1 equals absolute value of 1 plus 3. Most of my students then recognized that they needed to simplify inside the absolute value bars. So 1 plus 3 made 4, and that the absolute value of 4 is 4. So f of 1 is equal to 4. Similarly, f of negative 4 equals absolute value of negative 4 plus 3. Negative 4 and 3 gives negative 1. So f of negative 4 is equal to positive 1. Absolute value of x minus 8. Now the subtracting 8 is outside the absolute value bars. So we take the absolute value of the input 1, which is 1, subtract 8 and get negative 7. G of negative 4, absolute value of negative 4 is 4 minus 8, is going to give negative 4. Finally today, our students were given an opportunity to graph some simple absolute value functions. Again, in our textbook, we're only going to look at absolute value functions which have their vertex at the origin. We will see that there are some times that the absolute value function can be stretched or made more narrow, compressed. There are times that it can open up or open down, which we'll examine after checking their homework assignment on tomorrow. But this is the way that we went about graphing these absolute value functions. Our students are used to being able to make a table of values, but we're going to play off the fact that an absolute value function is symmetrical to limit the number of inputs that are required. In the case of this first example, we're going to use negative 1, 0, and 1. If I substitute 0 in for x, absolute value of 0 is 0 times 2 equals 0. I'll have a point at 0, 0. We recognize that the graph being symmetrical, the x value of 1 and negative 1 will have the same y value. Asked my students, which one would you rather substitute in? Almost universally, they wanted to substitute in a positive number. So we said the absolute value of 1 is 1 times 2 is going to equal 2. And we knew that by symmetry, we could reflect that across the y-axis, and when x was negative 1, y would be equal to 2 as well. So we placed our vertex at the origin at 0, 0. We calculated the value of y equals 2 when x was 1, and by symmetry, I know when x is negative 1, that y will also be 2. That's our graph of y equals 2 times absolute value of x. Using a trick that they learned in Algebra 1, we recognize that in example exercise number 4, whatever the absolute value of x is going to be divided by 2, multiplied by 1/2. So we're going to select negative 2 and positive 2 for our input values, because that'll give us an integer value for our output. So negative 1/2 times the absolute value of 2, which is 2, is going to give negative 1. My origin is going to be at the, my vertex is going to be at the origin 0, 0. And by symmetry, when x is negative 2, y is also going to be negative 1. And so this will be our graph, which not only opens down, but is wider as well. That's what our students practice today as far as graphing absolute value functions.